Hello again! Let's go ahead and compare and contrast the different types of chemical bonds and intermolecular forces. Atoms freely floating about in space are not considered molecules, elements, nor compounds. To be considered anything organized, such as a molecule, element, or compound, atoms must be bonded together via chemical bonds. So, what is a chemical bond? A chemical bond is just an attraction that holds atoms together. Emphasis on atoms, right? And so it looks something like this, where each of these purple lines represents a chemical bond holding the different atoms together within their respective molecule, element, or compound. Looking at our four main types of chemical bonds, well, first of all, starting basic, they are all chemical bonds. So they all have to do with an attraction that holds atoms together. Now, when you hear attraction, I want you to be thinking about magnets. Positive poles attract negative poles and vice versa. Atoms are not special. So thinking back to our protons and our electrons, these two also attract one another, right? Positive attracting negative, negative attracting positive. So we are going to be focusing mainly on electrons, as these contribute the most to forming our chemical bonds. So what separates polar covalent from nonpolar covalent, from ionic versus hydrogen bonds from one another? Well, each bond is variable in how strong they are, meaning how tightly they hold atoms together, and they're all based on electronegativity. They're based on the electronegativity of the atoms or elements they are bonding together. So, what's electronegativity? Electronegativity is formally defined as a chemical property that describes an atom's ability to attract electrons towards itself. But what does this exactly mean? To answer this, let's revisit our friend atom. Now, orbiting atoms are electrons, right? Which I've colored in red. Well, when two atoms become very close to one another, they begin to associate with each other, and their electrons basically become shared between the two atoms. Now, when this happens, which atom do you think will hold onto those electrons more tightly? Well, in this example, we see that the one that quote-unquote wins this electron sharing battle is the light blue atom. Because of this, we would call the light blue atom more electronegative than the dark blue atom. But why is this? Why is our light blue friend able to hold onto those shared electrons more tightly? And why is the light blue atom considered more electronegative? Well, it largely has to do with protons. Protons are positively charged. Therefore, just like a magnet, they attract more electrons, which are negatively charged. So it stands to reason that the more protons you have, the more electronegative you are, because you are able to attract more electrons towards yourself. Make sense? And we can see this to a degree in the periodic table too. Lucky for us, the periodic table is laid out by the number of protons each element has, right? Those numbers at the top of each square. And therefore, it is also basically organized by how electronegative they are. The low or weakly electronegative elements are found on the left-hand side of the table, such as hydrogen, lithium, and calcium. And the high or strongly electronegative elements are found on the right-hand side of the table, such as fluorine, chlorine, or iodine. So if sodium were to associate with chlorine to compete for their electrons, chlorine would attract the electrons more strongly to itself than sodium would. And therefore, we would call chlorine more electronegative. Also, as a side note, electronegativity also increases slightly as you move up the periodic table too. Here's a lovely cheat sheet with elemental electronegativity values that I suggest you either take a screenshot of or copy down in your notes. I do think this will help you moving forward. And like every rule in life, there are some notable exceptions. Here, those notable exceptions are our noble gases, which you find in the right-hand column of our periodic table. These guys are notably not electronegative at all, so just keeping that in mind as we move forward. Now, let's apply what we just learned about electronegativity with how it relates to our nonpolar covalent bonds, our polar covalent bonds, our ionic bonds, and our hydrogen bonds. Keeping in mind that the top three bonds that are on the screen are chemical bonds, while hydrogen bonds are actually something a little bit different, but we'll touch on that later.
So, ionic bond, covalent bond, James bond, there are just so many bonds. How can we possibly tell them apart? What determines which kind of bond will form between two atoms within the same molecule? Why electronegativity, of course. Let's break it down with an example. Let's say we are looking at two molecules and their difference in electronegativity is more than 2, like sodium and chlorine. Chlorine, in this example, would steal an electron from sodium. Sodium really wants to get rid of an electron, and chlorine really wants another one. So everybody wins. The result is a positively charged sodium ion and a negatively charged chloride ion. And just like magnets, particles of opposite charge, like sodium and chloride, have an electrostatic attraction. So these two ions stick together by forming an ionic bond. An ionic bond is a very strong attraction because it is happening between ions that have a formal charge. So, in an ionic bond, electrons are stolen, forming a very strong bond. But what if electrons are shared amongst atoms? Well, if the difference in electronegativity between the two atoms is less than 1.7, no electrons are stolen. Instead, the two atoms share the electrons. The electron from this atom feels the attraction from the other nucleus, and so does the electron from this atom. So the atoms share the two electrons to form a covalent bond. Covalent bonds can be polar or nonpolar. If the difference in electronegativity is not high enough to cause ionization, but is at least more than 0.5, like with hydrogen and chlorine, instead of completely stealing the electron, the chlorine will just sort of hold tightly those electrons in the resulting covalent bond. The more electronegative atom in a polar covalent bond pulls the electron density towards itself, and as a result of the slight electron excess, we call this atom partially negative, which we communicate to others with the symbol delta minus. The atom whose electron is getting pulled away is now slightly electron deficient, right? And therefore partially positive, or delta plus. What if the difference in electronegativity between the two atoms within a molecule is less than 0.5 though? Well, if the electronegativity difference is less than 0.5, the covalent bond is said to be nonpolar. In a nonpolar covalent bond, the electrons are shared almost evenly, or if we are looking at two atoms of the same element, they are shared exactly evenly. So the atoms will have no partial charges at all. Other than strange phenomenon like metallic bonding, these are the main ways that atoms bind to one another within a molecule. These are the kinds of intramolecular forces that I want you to know about. So remember, you can predict the type of bond that will form between two elements by comparing their electronegativities. If the difference is very low, like less than 0.5 or so, it will be a nonpolar covalent bond where the electrons are shared almost evenly. If the difference is between 0.5 to 1.7-ish, It'll be a polar covalent bond, where the electrons are shared, but one atom is kind of hogging, holding more tightly to those electrons. And if the difference in electronegativity is above 2, one atom will straight up steal an electron from the other atom, and you'll get ions that are joined by an ionic bond.
So, focusing in on our 3 chemical bonds, starting with our nonpolar covalent bond, which forms between elements with almost the same electronegativity. If we were to look on the periodic table at lithium and potassium specifically, we would say these would likely be nonpolar covalently bonded together if they were to come in close contact with one another. However, if we were instead to look at lithium and fluoride, we would not have a nonpolar covalent bond formed between these 2 elements because their electronegativity is just too different. Now, our polar covalent bonds are between elements with somewhat different electronegativity. So they're somewhat close together in electronegativity, but they're not almost the same and they're not very different. They're somewhere in the middle. A good example here could be between boron and nitrogen. These guys would be considered, if they came in close contact with one another, they would likely form a polar covalent bond. But if we were to instead take boron and fluorine, these would not form a polar covalent bond. Their electronegativity is just too different. And lastly, our ionic bond, which is between elements with very different electronegativities. If we were to use a similar example as before, like boron and fluorine, those would form an ionic bond between one another because their electronegativities are so different. However, boron and silicon would not. Those are too close in electronegativity, right? So those would not form ionic bonds. Now, hydrogen bonds are special and entirely different from the other 3 bonds we just discussed. Hydrogen bonds are not a chemical bond at all. They are what we call an intermolecular force. Inter meaning between, and molecular meaning molecules. So intermolecular forces, like hydrogen bonds, are bonds that form between molecules. So nonpolar, polar, and ionic bonds form within molecules. Hydrogen bonds form between molecules. For clarification, both of these interactions hold things together, but a chemical bond is an attractive force between 2 or more atoms within a molecule, whereas intermolecular forces are forces that hold 2 or more molecules together. In this example, we can see the difference in electronegativity between hydrogen and oxygen is about 1.4. So the chemical bond formed between them to make a molecule is a polar covalent bond, right? Since we see here that oxygen is more electronegative, that means that the oxygen atom is pulling more electrons towards itself than the hydrogen. Remember, electrons are negatively charged, so if the oxygen atom is pulling more electrons towards itself, that means it'll be partially negatively charged, more so than the hydrogen atom, meaning hydrogen here has a comparatively positive charge. So now let's say several of these hydrogen-oxygen molecules are floating around. The partial negative charge of the oxygen side of one molecule will attract the partial positive charge of the hydrogen side of the other hydrogen-oxygen molecule. This is our intermolecular force formed between the 2 molecules. Hydrogen bonds are a specific type of intermolecular force. To be a hydrogen bond, an interaction must meet both of the following requirements. Number 1, the bond must be formed between molecules that have hydrogen in them. No duh, right? And number 2, the atom within the molecule it bonds with must be more electronegative by 0.5 or more. such as that seen between the oxygen in one water molecule and the hydrogen seen in another water molecule, like we see over here to the right. Now, two things to note about our hydrogen bonds are that hydrogen bonds are very fragile. They're about 1/20th as strong as our covalent bonds. And hydrogen bonds are constantly breaking and reforming. This factoid will come into play a little bit later. Now, let's move on to our check-ins. So keep in mind this is check-in number 9, so make sure that you're looking at number 9 on your assignment. Is the bond between boron and oxygen atoms nonpolar covalent, polar covalent, ionic, a hydrogen bond, or none of these listed? For clarification, here is boron and here is oxygen. Number 10. Is the bond between these two molecules nonpolar covalent, polar covalent, ionic, a hydrogen bond, or none of these listed? Number 11. Is the bond between carbon and hydrogen atoms here nonpolar, polar, ionic, or a hydrogen bond, or none of these listed? Number 12. Is the bond formed between these two molecules nonpolar, polar, ionic, a hydrogen bond, or none of these listed? Keep in mind that this is just an example molecule. We would probably not find CH3 just floating around in nature. Excellent work! That concludes our discussion on chemical bonds and intermolecular forces.